first thing we're going to talk about is a matrix. These are going to be one of the main objects that we're going to be using in our course. And a matrix is simply a rectangular array of numbers, and we're going to surround those numbers by a set of brackets. They might be square brackets, like I have in this matrix below the definition. It's also acceptable to see matrices with circular brackets. So I may also write the matrix on the left like this. And that would also be an acceptable version of this matrix. Now the next thing we want to talk about are the numbers that are inside the matrix, and each of these numbers is called an entry. So for example, this number 2 is called an entry inside our matrix. And we want to be able to refer to those particular entries inside the matrix. So usually what we need is we need a way to describe the rows and the columns of our matrix. Okay, the rows being horizontal groups of numbers and the columns being the vertical groups of numbers. So I could divide this matrix up at the bottom into its 6 entries. Alright, so for example here we have row 1 are the numbers 2 and 1. Row 2 are the numbers -1 and 2. And finally, row 3 is 0 and 5. And similarly, we have 2 columns. Our first column is 2, -1, 0. So this is column 1. And we have a second column here, 1, 2, 5. Okay, so we use these numbers to describe the size of the matrix. We talk about how many rows does it have and how many columns does it have. So this matrix here in our example has 3 rows and 2 columns, so we would often say it is 3 by 2. The next thing we're going to talk about are 2 special forms that our matrices might come in. The first one is called reduced row echelon form, and sometimes this is shortened down to RREF. We say a matrix is in RREF if it satisfies all 4 of the following conditions. So the first one talks about full rows of zeros. If we do have a full row of zeros, it has to be at the bottom of the matrix. And if we have more than one full row of zeros, they're all at the bottom stacked on top of each other. The second condition is that if we have a row that's not full of zeros, the first number that we read from left to right has to be the number 1. And we call that number 1 a leading one. The third property is that every leading one inside of our matrix has to be below and to the right of any leading one that's above it. And the last property is that all of the entries above and below a leading one have to be 0. So this includes all of the entries in the column containing that leading one. To help us understand the definition of reduced row echelon form, let's take a look at a couple examples. And what we're going to do is we're going to check to see if the matrices satisfy all 4 conditions of our definition. So let's start with number 1. Number 1 says, if the matrix has a full row of zeros, it has to be at the bottom of our matrix. And when we look at our 3 by 3 matrix here, there are no full rows of zeros. So number 1 is satisfied because it does not contain any full rows of zeros. Property 2 says, if we have a row that's not full of zeros, the first number has to be the number 1. And we call this number a leading one. So if we look at row 1, the first number that we hit that's not 0 is number 1. And similarly for row 2 and for row 3. So property 2 is satisfied. The first number that we hit reading from left to right is the number 1 in any given row. The third property says that any leading one has to be below and to the right of any leading one that's above it. So let's take a look at our 3 by 3 matrix. We have 3 leading ones, and the second leading one is below and to the right of the first. The third leading one is below and to the right of the second. So all of our leading ones are below and to the right of any leading one that is above it. So property number 3 is satisfied. And the last thing we have to check is property 4, and that says that all entries above and below our leading ones have to be 0. And what I usually do is, if I have a leading one, I take a look at the column that the leading one is in, and I check to see that all of the other entries in that column are equal to 0. So here's the column that our first leading one is in green, and we see that all of the entries below our leading one are 0. If we move over to the column that contains our second leading one, all of the entries above and below this leading one again are equal to 0. And finally, checking the last column that our third leading one is in, all of the entries above this leading one are 0. So we can conclude that the fourth property is true. All of the entries above and below our leading ones are 0. So we would say that this matrix is in reduced row echelon form. Excellent. So let's quickly go through a couple more examples here so you get the feel for how to do this fairly quickly in your head. Okay, so we come to this matrix. We'd like to know if it's in reduced row echelon form. First thing we do is we see if there are any full rows of zeros. And yes, this one does have a full row of zeros. Then we ask ourselves, is it at the bottom? The answer is yes. So property 1 is satisfied. The second property has us looking for what are called the leading ones. So we look at the rows that are not full of zeros, and we check to see that the first number is a 1. And that's true for all of the rows that are not full of zeros. The first number we read from left to right is a leading one. The third property is that any leading one must be below and to the right of a leading one above it. In this example, we only have one leading one, so there are no other leading ones to compare this one to. It automatically satisfies property number 3. And the final property, property 4, all we do is we take a look at the columns containing our leading one. So in this case, we have all zeros below our leading one, so property number 4 is satisfied. Take the time right now to pause this video and go through the 4 properties regarding this new matrix that we have here, and determine if you think it's in reduced row echelon form. Alright, did you get that it wasn't in reduced row echelon form? Let's see why. So first property talks about full rows of zeros. Our matrix doesn't have any full rows of zeros, so it automatically satisfies property number 1. Property 2 deals with the leading ones, so we check each row, and we see if the first non-zero number is a 1, and that's definitely true. We have 2 leading ones, 1 for each row. Now the third property says each leading one has to be below and to the right of a leading one above it. And our second leading one is definitely below and to the right of the first. So the third property is satisfied. The final property deals with the columns. So we circle a column that contains a leading one, and we see if all of the other entries are equal to 0. And here's where we're going to run into problems. So take a look at this second column. Okay, we have a leading one in column number 2, but not all of the entries are equal to 0. And it's this number 2 up here that's causing us the problem. So it does not satisfy property 4. This matrix is not in reduced row echelon form. The second special form our matrix could be in is called row echelon form, and this one's usually simplified to REF. We say a matrix is in REF if it satisfies the following 3 properties. The first one is if the matrix has a full row of zeros, it has to be at the bottom. The second one is, as we read from left to right in a non-zero row, the first number we hit must be a 1, and these are the leading ones. And property 3 says that a leading one must be below and to the right of a leading one above it. And I think the most important thing to notice here is that these are the first 3 properties of reduced row echelon form. The only difference between our REF and REF is that fourth property. REF does not require that we have zeros above and below our leading ones. Now let's head back to that example we had previously just so I can illustrate that fact. Now here, remember that there are no full rows of zeros, so property 1 is going to be satisfied. We take a look at our leading ones, so each row here has a leading one. So property 2 is satisfied. And we also have that the second leading one is below and to the right of the leading one above it, so property 3 is satisfied. But here we don't have property 4 if we're only looking for REF. So even though this matrix is not RREF, it is REF. And that's because we don't have to check the fourth property. So this leads us to one of the big observations here, and that is that if a matrix is in reduced row echelon form, it automatically has to be in row echelon form. That's because if it's in RREF, it satisfies all 4 properties, specifically the first 3 properties which we need in order for the matrix to be in REF. Now a couple questions might come up. The first question might be, if we're given any matrix, is it possible to change it into RREF or REF? We're going to answer that question in the next lesson. And a second question that may have come up is, what is the importance of reduced row echelon form in row echelon form? And I'm going to save that question for a future lesson. Alright, my little epsilons, stay positive.